All right, today we are starting section 6.4. We are going to start talking about our special quadrilaterals. Some of them you are already going to be somewhat familiar with because you went to elementary school and they talk about shapes there too. For our warm-up, let's review some of our parallelogram properties. So on the first one, we are finding the value of x. How are we going to do that? We could use the fact that this is a quadrilateral and the fact that all four of these angles need to add up to what? 360. Or because we know it's a parallelogram, what do we know about opposite angles? They're congruent, so we could set 3x equal to 90. Either way works. Both of them are totally valid. In my opinion, this one's a little quicker, but either way would work. Okay, so we divide by 3, x equals 30. Is that enough? Okay. All right, on the next one. What do we know about opposite sides? In a parallelogram, they are also congruent. So we are going to set 6x equal to 18, divide, and we get x equals 3. All right, we'll keep moving then. So we are going to talk about rhombuses, rectangles, and squares specifically today. Those are our special quadrilaterals. A rhombus is a parallelogram with all sides congruent. So that's, by the definition, what has to be true about it. It has to be a parallelogram. So all the properties of a parallelogram hold. But in addition to that, all the sides are congruent. So not just opposite, all four of them. So we could mark that in our picture. I'll give you a minute to finish writing before we talk about the properties and mark that in our picture as well. Okay, so we know that all of the sides have to be congruent to each other for a rhombus. All the properties of parallelograms still hold, but I'm not going to mark all of those because then this diagram would get a little too busy. But things like opposite angles being congruent, that's still true. Consecutive angles being supplementary, that's still true. But the extra properties we add when we know that it is for sure a rhombus would be that the diagonals bisect a pair of opposite angles. So if I were to draw in the diagonal here, that diagonal bisects those angles. And both diagonals do that. I don't know that I'll draw that in. So we end up with 4 littler, smaller, congruent angles. Also, each diagonal is a perpendicular bisector of the other. We already knew that diagonals would bisect each other because this is a parallelogram. But when we add in that perpendicular bisector part, what does that mean? What does perpendicular mean to us? They form right angles. So not only do these diagonals bisect each other, they also form right angles. And of course we know if there's one right angle there, there are really how many? 4 of them. All 4 of them would be right angles. If you want to mark the pieces congruent to each other, you can. That would be true in any parallelogram. But in a rhombus, those diagonals will also form right angles with each other. If you want to go ahead and mark your other angles congruent on the outsides, that pair of opposite angles, you could do that as well. But it gets to be a little busy when we try to mark everything in a small space. Questions about the properties of a rhombus? Okay, if you need to make a note of it or highlight that word parallelogram in the definition, you could say also has all properties of a parallelogram. It's important to remember. Anybody need more time on this slide? Okay. Next up, we have the definition of a rectangle. It is a parallelogram with 4 right angles. A rectangle is probably a shape that you're familiar with. Oh, sorry, too fast. Bring it back. So a rectangle will have all the properties of a parallelogram. It will also have all 4 angles that are right angles. And its extra property is that the diagonals are congruent to each other. All right, so again, we have all the properties of a parallelogram. So if you wanted to mark some of those, you could, like opposite sides being congruent. Of course, opposite angles are already congruent because they're all right angles. This time, our extra property, the diagonals are congruent. So if I were to draw in my 2 diagonals, it's kind of hard to mark that they're congruent on here. So if I were to name this rectangle A, B, C, D, I would know that AC is congruent to what? BD. Those are my 2 diagonals. But because it's a parallelogram, the diagonals already do what to each other? Bisect each other. So what that really means is that all 4 of these little pieces that meet or intersect in the middle, all 4 of those little pieces are congruent to each other. So the whole diagonals are congruent to each other, and each little segment of a diagonal is congruent to each other little segment of a diagonal. Last up, we have a square. It is again a parallelogram. It is both a rectangle and a rhombus, which means it has 4 congruent sides and 4 right angles. All the sides are the same, all the angles are 90 degrees. All right, if I've got a square, all the sides are the same, all the angles are right angles, I'm not going to put in my right angle marks right now, just because that'll get a little confusing once I draw in my diagonals. So if I put the diagonals in there, our special property states that the diagonals form 4 congruent isosceles right triangles, or 45, 45, 90 triangles. And this makes sense if we think about the fact that a square is both a rhombus and a rectangle. If it's a rhombus, I know that the diagonals intersect to form what kind of angles in the middle? Perpendicular lines, so they form right angles. So I know that in here I've got a bunch of 90-degree angles if it's got the properties of a rhombus. If it has the properties of a rectangle, I know that the diagonals are congruent and bisect each other. So kind of like on that last one, we could mark all of these little pieces congruent to each other. So if you look at just this top triangle that's formed, it's an isosceles because 2 sides are the same, right, because it's a 90-degree angle triangle, which by all of those other rules and properties we've learned means that these 2 angles have to be 45 degrees each. This ends up being true for all 4 of these little triangles that we made. Do we have questions about that? Okay, so when it's talking about those 4 congruent isosceles right triangles, they mean this one on the top, the one on the bottom, the little one on the left, the little one on the right. Those are the 4 triangles. We also end up with bigger 45, 45, 90s. If you were to just draw in one diagonal, it would form larger 45, 45, 90s. But if you put in both diagonals, that's when you get all 4 little ones. Questions, concerns, need more time on this slide before we talk about all these properties together. Okay, on the back, we start in with some examples. I will give you a moment to write in what we are told about it. You'll notice on your notes we're also told what type of special quadrilateral it is. You're told this first one is a rhombus. I'm going to go ahead and label it with the information they gave us off to the side. So AX is 12, DX is 5, AD is 13. Now for a problem like this, it probably took you just as long to label the diagram as it will to answer these questions. What is the length of BX? Why is it 5? Okay, so diagonals bisect each other in any parallelogram, so BX would have to be the same as DX. BX is 5. CX, 12, same idea, different diagonal. So CX would have to be 12 if AX is 12. BC is 13. DB, 10. How'd you get 10? Okay, add them together, 5 plus 5. AC, 24. Again, add the 2 pieces together. And DC is 13. So in a rhombus, all the sides on the outside are congruent. So AD, DC, BC, and AB, even though we didn't name it, would all have to be the same. Okay, we again have a rhombus. In a rhombus, the diagonals do what to the opposite angles? Bisect them. So angle 1 better measure 32 degrees. Okay, so if this is a diagonal of a rhombus, it's bisecting this angle. So angle 1 has to be 32 degrees. The diagonals are also what to each other? Perpendicular, which means angle 2 should measure 90 degrees. Diagonals are perpendicular. All those angles in the center are 90-degree angles. So how could we figure out angle 3? Yes, you're getting at the right idea. Why could we do 90 minus 32?
Oh, because they're 45. No.
Inside of any triangle, all the angles should add up to? 90. 180. So if you already know one's 90, the other two have to add up to 90. So the easier idea to remember is that if we've got a triangle here with angles 1, 2, and 3, all three of those would have to add up to 180. Now, if you take 180 minus the right angle right away, you're already only left with 90. So when you subtract off the 32, you get 58 degrees for angle 3. Questions about how we got there? Okay, what does that mean for angle 4? Why is it 58? Yes. Can you tell me why? The diagonals bisect those angles. So angle 4 would be congruent to angle 3. So then we are asked about the measure of angle KTN. Oh, that's not very pretty. KTN. So that would be this whole angle up here. How would we figure that out? Good. So the big angle at T should be congruent to the big angle at E, because they are opposite angles inside of a parallelogram. So if we add 58 and 58, we get 116. So that would have to be the measure of KTN. Now TNE is a little bit easier. TNE means the big angle at N. What would that be? 64 if we add those little 32 angles together. Notice that our consecutive angles would be supplementary. If we were to add these two angles, it would be 180, or these two, or those two, these two. Questions, concerns, need more time with example 2. Okay. They told us that number 3 is a rectangle. Okay, a couple of these sides should be really easy to identify right away. Which ones are easy to know right away, Crescencio?
DC and AD.
Okay, DC would be 4 and AD would be 3, right? Opposite sides are going to be congruent in a parallelogram. So those ones are easy. The other ones aren't terrible. AC is a diagonal. So, if we were to ignore the other diagonal for just a moment, if I were to just kind of ignore that other one, what do I know about the big angle at B? It's a right angle because this is a rectangle. All of them are right angles. So if I have a right triangle and I'm missing a side, which happens to be a diagonal, how could I find it? A squared plus B squared equals C squared. We could go back to that formula from the Pythagorean theorem. Are we all following? Okay. So A squared plus B squared equals C squared. In this situation, when I'm trying to find the diagonal, which letter, A, B, or C, am I trying to find? C, because it's across from the right angle. So a diagonal is going to be like a hypotenuse for a right triangle if we're working with a rectangle. What do you want to plug in for A? 4 squared plus 3 squared equals C squared. This is actually a Pythagorean triple. It's going to be 5, so 16 plus 9 is 25. Square root them, and C, or the diagonal, has a length of 5. So that's what we get for AC. Questions about how we got that? Okay, so I'm going to bring back my other diagonal so we have the full diagram there. What do you think BD is? Why? Diagonals are congruent inside of a rectangle, so the other diagonal, BD, would also be 5. You don't have to do your Pythagorean theorem again. Last one, CX. 2.5 or 2.5 or 5/2, however you want to write it. This is still a parallelogram, so the diagonals still bisect each other. So each little piece, AX, BX, CX, and DX, would all be 2.5. Questions, concerns? Need more time with our rectangle, our first rectangle. We ready? Okay, on we go. This one's also a rectangle, I believe. Now we're going to look at the angles. All right, another rectangle. This time we're looking at a bunch of angles. We were only given one angle in the diagram directly. We'll have to work on finding the other ones. There are probably multiple ways you could go about finding some of these angles. I would recommend starting with angle 1. Anybody know how we would find angle 1? Why subtract from 90? Okay, all of these angles in the corners, the big angles, have to be 90-degree angles if it's a rectangle. Our corners all have right angles in them. So for angle 1, we could take 90 minus 21. We would get 69 degrees. To get angle 2, it's actually, in my opinion, easy, but maybe a little bit tricky. Because in order to get that angle, we need to think about our diagonals. What do we know about all of the pieces of the diagonals? Like if I were to break it up into 4 pieces, what do we know about all 4 of them? They're all congruent inside of a rectangle. So these are all congruent to each other. That means that on the left side here, we form a little isosceles triangle. If this is an isosceles triangle, what has to be true about angles 1 and 2? They have to be congruent because they are across from the sides that are congruent, which means angle 2 is also 69 degrees. Are we following the logic on that? Okay, a lot of these are not going to be challenging to find mathematically. It's more challenging to think through all of the properties that you know. In order to find angle 3, what do we need to do? Subtract what from 180? Okay, we need to subtract those other 2 angles, 1 and 2, from 180 to get the last angle inside that little triangle. So 180 minus 69 is 33? 43? That doesn't seem right. 42? Okay. 42 degrees. You okay with that? How could we then find angle 4? We could do it a similar way that we did for angles 1, 2, and 3, but that would mean we would have to find which angle first. 5. And that's fine. We could do that. But can we think of another way that we could find 4 right now without talking about 5 first? Why? Because why?
Because it's supplementary.
They're supplementary because they make up a 3 and 4 make up a straight line. They're a linear pair. Okay, do we see that? 3 and 4 make up that straight line right there. So you could talk about angle 5 first, and that wouldn't be too hard. We'll do that in a moment. And then find angle 4 that way. Or you could just subtract angle 3 from 180 to get angle 4. So if we take 180 minus 42, we get 138. And really, we could have filled in the measure of angle 5 from the very beginning. It would be 21. It has to be congruent to the angle they gave us because, again, we have another isosceles triangle at the bottom. Gotta use your brain a lot on these. Your calculator maybe a little, but your brain a lot. Questions, concerns, need more time? We've got one more example. We're ready for it. Here we go. Lots of things to find. Oh, sorry. There we go. Lots of things to find, and only one little piece of information is given to you. However, you were told that this is a square, which is important to us. That actually tells us a lot about the diagram from the very beginning. A square is going to have all the properties of parallelograms, of a rhombus, of a rectangle. It's got lots of properties. Some of these will be really easy to fill in right away. Did they give us any of the easy ones? Like AB. What's AB? 12. Okay, and a square, all the sides are congruent. Let's see. All of those on the inside. They labeled BC for us, so I think it's a little funny they asked for it. BC is 12. Okay. In my personal opinion, it's going to be easier to talk about DB or AC before we try to talk about any of the ones that go to X. DB and AC are what? They're perpendicular. What do we call them in general, though? They're the diagonals. Because this carries the properties of a rectangle, we know the diagonals are going to be congruent. So we know right away that DB and AC should end up being the same thing. So let's focus on AC. So I'm going to redraw this off to the side just roughly. I know that all the sides are 12. Here's my A, B, C, just so I don't have to erase a bunch of this stuff. What kind of angle is at B? A right angle, because it does have the properties of a rectangle. So we could find our diagonal using Pythagorean theorem. Or if you remember your special right triangles, this big triangle is a 45, 45, 90. Remember, because it has the properties of a rhombus, the diagonal bisects those 90-degree angles in the corners. Does anybody remember how to find the hypotenuse of a 45, 45, 90? Beautiful. H equals a leg times root 2. Do we remember talking about that? It's been a minute. It's coming back. Okay, if you don't remember that, then yes, you could just use your Pythagorean theorem. You'd end up getting the same thing. But in this case, our hypotenuse, or that diagonal, is equal to what root 2? Whoa. 12 root 2. Are we all okay with that? Questions, concerns about it? So AC has a length of 12 root 2, and so does DB. Both the diagonals have a length of 12 root 2. What do we know about DX, AX, BX, and CX? They're all going to be the same thing, because if a square has the properties of a rectangle, we know that all of the pieces of the diagonals are congruent. And because it's a parallelogram, we know that the diagonals do what to each other? Bisect. So what are all of those going to be? What are they going to be? 6 root 2. So they'll be half of the 12 root 2. 6 root 2, 6 root 2, 6 root 2. So we just had to cut a diagonal in half. 12 divided by 2 gave us 6. We have questions about any of the lengths that we had to identify. Okay. Probably the trickiest part about talking about the angles is remembering how we name angles is important. So if we're talking about angle AXB, is that going to be on the outside or the inside? It's on the inside. AXB is here on the inside. Anybody know what it is? Crescencio? 90. Because it is a rhombus, the diagonals are, special P word, perpendicular to each other. It's got to be a right angle. Next, we're talking about angle XAB. Is that going to be on the inside or the outside? On the outside. Start at X, then go to A, then over to B. What's it going to be? 45 degrees. In a rhombus, the diagonals bisect those angles. So what about XBA? Also 45. They just switched it to the other side, but it's still a diagonal bisecting an angle, so still 45 degrees. Lots of properties. Questions about any of them?